Hey everyone, in today's video we're going to still be working on finding the volumes of three-dimensional solids, but the way that we create those solids is going to be a little bit different. Before we learned to do this by building up cross sections on a base, now we're going to be taking curves and revolving them about the x or y axis. So we're going to learn what that process is going to look like in this video. Now, we're going to make some changes to these notes. The way I think through this is a little bit different than what's in the notes. Either way, it gets us to the same place, but I like this other method because we can kind of connect it to what we've already been doing. So we're going to skip this first part here, and we're going to jump down to where it says finding volumes of solids of revolution. So again, the big idea for us here is that sometimes we can find the volume of a three-dimensional shape by taking a curve and rotating it around a given axis. And we kind of did a demonstration of this in class yesterday. So to do this, we imagine dividing the solid figure into circles that have been turned on their side. So for example, if I made slices through here, if I looked at each individual slice, it would be a circle. So then we're going to find, I'm going to say, the area of each circle. And just like we did with cross sections, we need to add all those areas together. Now I've got a bunch of circular cross sections that I need to add together. And since we're adding, we know the most efficient way to do this is to use an integral. So the kind of nice part here is once we can visualize what we're doing, we're really just adding up a bunch of areas, and for volumes of revolution, those areas, we're always going to be finding the area of a circle. So we call this method the disk method because each, I'm going to say cross section, looks like a thin disk if we could view it individually. So if we were able to slice through here, each of those cross sections would look like a disk. So here's our general process for finding these volumes, and then we'll work through several examples. So the first thing we want to do is sketch a very good graph. This is going to give us a good idea of what we're working with and help us identify the radius appropriately. So then we're going to draw in the other half of the curve. So for example, if we look at this picture here, in this example, this would have been the curve that we are interested in rotating. So when we do this in our paper, if we can draw in kind of the reflection of that curve, which is down here, then we can visualize what one of those circular cross sections would look like. And that's what was done here. So as this is revolved, it creates this circular cross section. So it says draw one circle to help visualize, and I'm going to say here, help visualize the solid. Okay. Then we're going to identify the radius of the, I'll skip this, of the circle. So in this case up here, if I were finding this curve, my radius would be the distance between that curve and the x-axis. So in this picture, that would be my radius. Then we're going to set up our integral and we'll solve. Now, I know at this point, this doesn't probably help us a whole lot, so we'll go through those steps and kind of reference them each time we go through an example. So let's look at what this is going to look like. So number one is a calculator problem, so you'll want to have that out. So it says here the region between the graph of f of x equals 2 plus x cosine of x and the x-axis, so there's my region. So it's between this curve and the x-axis. It's giving me an interval here, and it's telling me it's revolved about the x-axis to generate a solid, and we're looking for the volume of that solid. So the first thing I'm going to do is, like it says in step 1, is to sketch a really good graph. So I'm going to go ahead, I got some stuff to clear out. I'm going to type this into my y1. And let's see, I'm getting a graph here. I'm going to change my window because I know I'm going in between -2 and 2. So I'm going to change my x min and max. All right, so my picture is going to look like this. Let me scooch this over the side. Sorry about that. So it kind of looks like this, I guess. Something like that. Okay, so that's kind of the sketch of my graph over the interval that I'm looking at. So we said we're going to sketch a graph. In step 2, we said we're going to draw in the other half of the curve. So I'm going to kind of imagine if I could reflect this here, right? It would look something like this if I could draw in that other half. And then what I like to do, and you won't have to do this every time, but we can kind of imagine, right? This would be like one cross section. So you can see it almost looks like a vase on its side. So that's what I'm going to get by revolving this region here about the x-axis. So now I've got an idea of what I'm looking at. So now, since we're adding up circles, I know the area of a circle is pi r squared. Right? Each of these cross sections is going to be a circle. So if I can add up all those areas, I'll get the volume of this solid. So now we need to think about what our radius is. Since I'm revolving about, let me move this over, about the x-axis, my radius in this case is going to be the top minus the bottom, which we've worked with a lot at this point. So the top is this curve here. So that's my 2 plus x cosine of x. The bottom is just the x-axis here. That's what I'm revolving about, the x-axis. So that's just going to be minus 0. And maybe I'm going to highlight this in green. This will be more important later. So I kind of like to highlight the axis that I'm revolving about. Okay, so my bottom is 0, so I know my radius is just 2 plus x cosine of x. So now I'm going to use an integral to add up all of these areas. So my volume is going to be, I know I need a pi. Since that's a constant, I like to pull it outside of the integral. So pi times the integral of, I need my radius, which is 2 plus x cosine of x. And then I need to square it. Right? This part alone is just my radius, but I know I'm finding the area of circles and adding those, so that's an r squared. And then I need my dx. One thing I should have done here, I usually like to mark in that this here is my radius from top to bottom. So now since this is a calculator problem, we can just go ahead and type that in. So let's see, I've got pi math 9 for my integral. Oops, I didn't put in the bounds. We're going from -2 to 2. All right, so -2 to 2, it's right in the glare there. Of, let's see, 2 plus x times the cosine of x. And I'm going to square that, and then dx. And I get as approximately 52.429. Again, when we're using our calculator and approximating, we always put it to 3 decimal places. All right, so that is how we do problem number 1 when we're revolving to find these volumes. All right, number 2 now, this is no calculator, so we can put those aside. Asks us to find the volume of the solid of revolution generated when this curve, okay, so the region between this curve and the x-axis, okay, over the interval from -1 to 1, and again we're revolving about the x-axis here. So the first thing I need to do is sketch a graph of this curve. Let's see, so I'm going to plot some points here. I know when x is 0, my y value is 4. So 0, 4. If I have a positive 1, my y value is 3. -1 gives me the same value. And then if I plug in 2, it's 0. So this is not a great picture. It's way too flat at the top. That should be somewhere here. All right. So we've got that parabola opening down. This is a terrible parabola, so you'll have to excuse that. That looks a little better. All right, and so we're revolving over the interval from -1 to 1. So this region here revolved about the x-axis. So what I want to do here, this is our region that we're going to be revolving. So if we think about, again, visualizing what's happening here, if I kind of reflect this, it would look something like this. And then our cross sections would be these circles here. And I could do one that ends. Some of us, that helps us visualize. So now my radius, right, is going to be from the top curve here, again, to the bottom. So we're still adding up areas. So all our cross sections are circles. That area is pi r squared. So now we know our radius, again, is going to be top minus bottom. And in this case, my top function was the -x squared plus 4. Our bottom is the x-axis, which is just y equals 0. So I know my radius is -x squared plus 4. So now we're going to use our integral to add up all these areas. So my volume is going to be, I'm going to pull my constant pi out front, times the integral. Our bounds are -1 to 1. I'm going to take my radius, -x squared plus 4, and I need to square that, and then I have my dx at the end. Again, this was my r, and I needed pi r squared for the area of that circle. So now this is no calculator, so now we've got to do some work here. First thing I'm going to do is I'm going to expand this. So pi from -1 to 1, the quantity of -x squared plus 4 squared, that's going to give me x to the 4th, let's see, minus 8x squared plus 16. Now again, I haven't anti-differentiated yet. I just rewrote the integrand. So now I'm going to find the antiderivative. So I'm going to put my pi out front. My antiderivative of x to the 4th is going to be x to the 5th over 5. This will become minus 8 thirds x cubed, and then this becomes 16x. I have my plus c, and I'm integrating from -1 to 1. So now I've got, let's see, 1/5 minus 8 thirds plus 16 plus c minus, and then in parentheses, if I have a -1 here, I've got -1/5. This is going to become, a positive 8 thirds, and this will be a minus 16 plus c. And now we've got some simplification to do. So I know my c's are going to cancel. If I look at my 1/5, I'm going to have 1/5 minus a -1/5, so I'm going to add those. So I'll have pi times, that's 2/5. I have -8 thirds. This has become a -8 thirds, so minus 16 thirds. And then 16, that's going to become a plus, so plus 16 is plus 32. So it looks like I'm going to have a common denominator here of 15. So let's see, I multiply by 3, this becomes 6/15. I have to multiply by 5, so that becomes 80 over 15, if I did that right. I hope. And then 32 times 15. I'm going to go over here because I don't know off the top of my head. So 10, that's 160, 2, 3. It doesn't look. Okay, yeah. So it looks like 480. So plus 480 over 15. And so now I'm going to simplify. That's going to give me a negative 74 plus 480. So it looks like 406 over 15. So my exact volume is 406 pi over 15. Now I know it's easy to get lost in all this anti-differentiation and arithmetic here, but again, I want us to be focused on making sure we understand this setup here. All right, we're going to do one more together because it has a little bit of a twist to it, and then that will be good for this video. All right, so number 3 says to find the volume of the solid of revolution generated when this curve here, x equals negative y squared plus 1, and the and the y-axis now. So let's see, we've got x equals negative y squared plus 1, and the y-axis. Now here's my interval, and now we're rotating about the y-axis. So let's get a picture of what this is going to look like. And I'm probably going to have to make a table here. I'm not exactly sure what this is. So let's see. I'm going to make a little XY table. So let's see, when y is 0, I get that x is 1. And then if y is negative 1, let's see, it's going to give me 0 for x. Maybe I'll try when y is 1. That still gives me 0. And maybe I'll just do negative 2 and 2 to get a couple more points. So negative 2, negative 4 plus 1, that's going to give me a negative 3. If I plug in a positive 2, that also gives me a negative 3. So now I've got enough to go on here. So I've got 1, 0, 0, negative 1, 0, 1. And then what do I have? Negative 3. And 2. So it looks like this. All right, so there's my graph. So now it's the region bounded, let's see. Okay, between this curve and the y-axis, but now it says between y equals 0 and y equals 1. So that's really limiting us to this region here. That's what's being revolved. Okay, and we're revolving about the y-axis here. So again, if I'm thinking about what this actually looks like, I could reflect this over here. One of my circular cross sections would look like this. Looks like maybe like half a lemon or something. So the big idea here now is since I'm revolving around the y-axis, I need to make sure that I integrate with respect to y, which is really nothing new to us. You did this with area. So we still are adding up circles, but now when we think about our radius, and this is going to be really small, so sorry about that. My radius would fit in there, but now my radius is actually right minus left. And again, we're integrating with respect to y, so everything should be in terms of y. So my right boundary here is my curve, negative y squared plus 1. My left is just x equals 0, so that's minus 0. So my radius is negative y squared plus 1. So now, again, our goal is to add up all the areas of these circles, which we do by using an integral. So I have pi from my area formula. We know our y bounds are from 0 to 1. We're going to square that radius, negative y squared plus 1 squared. Again, that's our radius squared. And then we have our dy. Now, this is a no calculator problem, but for our purposes here, instead of going through all this math again, we're just going to use our calculator to estimate this value. But be aware this is one that you would be expected to be able to do without a calculator. So let's see here. I've got pi math 9, whoops, from 0 to 1, negative x squared plus 1 quantity squared, and then that, and I get approximately 1.676. Okay, so hopefully that gives you a pretty good understanding of what's going on here. The rest of the examples we'll do in class together just to make sure everyone's feeling pretty comfortable and you get a chance to ask questions. And then we'll move on to practice from there. All right, thanks. See you back in class.